Good morning, everyone, and welcome to this session on digital signatures. Our first talk in the session will be on accelerating SLH DSA by 2 orders of magnitude with a single hash unit by Markku Juhani Saarinen. Markku, the floor is yours.
All right, thank you very much. So, reminder of what SLH DSA is. So this is algorithm known as Sphinx Plus, standardized as FIPS 205. The standards came out last week, originally designed by many people, including Andreas Hülsing. It is a stateless hash-based signature, so this is unlike XMSS and LMS. You can do a lot of signatures with this, 2 to 64 signatures before losing security with a single secret key. It is quite complex. So on the right-hand side here, I tried to draw a picture of the entire SLH DSA. So it has main parts which are kind of disconnected. So we would have this few time signature scheme called force. We would have layers or a hypertree of XMSS signatures, and each layer of these hypertree has a Internet's one-time signature and then followed by a Merkle tree. So together these are called XMSs in the standard. Each one of these little parts in here create part of the signature in a sort of a linear fashion. So the first part of the signature itself is actually the force, the top few time signature scheme, followed by each one of these XMSs layers. Now there was a modification last week on the final standard that came out. So there, what was previously Sphinx Plus became an internal Sphinx Plus, and what they added is an external layer on top of it. So this external layer, which basically does the padding or pre-hashing, is not fully testable yet, but I did run the test vectors that are available from NIST ACVP against the implementation that I'm talking about, and that is still apparently intact. So they didn't change the core things. So there's an artifact of this, and it is actually still doing exactly FIPS 205. Now, like a little bit of a reminder about the use case of such a thing. So you wouldn't probably use this for interactive authentication, but like in a logging onto a website and a website signing some challenge or something like that. No, that wouldn't be a use case. So typically these things would be sitting on a root of trust unit on a SoC. So this is a separate part of a system on a chip unit, kind of independent from the main processor. It would have its own processor. Examples of these are OpenTitan, which is kind of related to Google, and then we have Calyptra, which is actually used by many vendors. So it was Microsoft, NVIDIA, who else? I think Google, yeah, Google is there as well. So these actually do the secure boot part of SoC. So SoC could be, in case of NVIDIA, it could be a GPU. It could be a like a mobile phone from Google. It could be something like a PlayStation from Microsoft. But each one of these, like first when you boot up, control goes into a root of trust unit, and then after it's happy, it wakes up like all of the other components that you have, your processors and such. So this device that I'm describing is for that. And there's a latency requirement. Your boot or especially your wake up time, in case you need to do a signature in wake up, needs to be in milliseconds. So you are saving power, you are sleepy mode, and then you want to wake up and verify your integrity. That's why the verification, for example, needs to be fast. These units also need to do signing for attestation. So that's why having something like LMS or XMSS here is really, really tricky. So we can't really use those. So that's why the only alternative would be to use dilithium, and in there are cases where you can have that. But anyway, so that's the design space for this device. So what the design has is all parameter sets. So there's 12 parameter sets in the final. There's both SHA-2 versions. There's shake versions. So I put all of the hardware in there, and it supports all of those. So this has done before. So previously, when people implemented this, they had a general purpose hardware accelerator. So these units are usually just designed to hash input data rather than specifically designed to support hash-based signatures. So in hash-based signatures, of course, 99.999% of the hashes computed are of other hashes. So it's a completely different kind of function that you would like. And so because of this particular thing, because of optimizing for this use case, this ends up being something like 10 times faster than the current hardware units in applications like OpenTitan. So this is quite significant. So the hardware size didn't grow much. But the trick is really to do certain steps in the algorithm directly in hardware, like Winternitz iteration. I'll come to that later. Also, what I have here, previously there was like a folk assumption that these things are side channel secure somehow. So they are of course timing side channel secure, but actually they do leak on emission and power channels quite a lot. So I put in some countermeasures in there, and this paper also has like an analysis of the sensitivity, like which variables are sensitive, which you actually need to protect, and which are not so important. So that is another contribution. So we are passing like the standard leakage assessments with this implementation. It's publicly available. I have this URL later on in the slides multiple times. Now, just to give a handle on like how much faster it is. So in PQM4, which is the pretty much standard benchmarking case, has Sphinx Plus. Of all of the other algorithms they typically benchmark it by running 100 iterations, but because Sphinx Plus is so slow, they typically only run 3 iterations. So that's in tens of millions, sometimes a billion cycles on a typical microcontroller. Then we have the AVX2 implementation. So these numbers are from the specification. So these are from the authors themselves. So that's of course quite a bit faster because you are using AVX2. You have like these SIMD optimizations. And then on the third line here, we have a recent paper in hardware implementation where they also tried to do these optimizations. So even compared, of course, to the original one, we have the 2 orders of magnitude speed up to a microcontroller compared to a high-end PC. We have, 20 times faster. But even compared to a hardware implementation for the same use case, which has not been specifically optimized for SLH DSA or hash-based signatures, just for hashing, it's 10 times faster, roughly. And you save that amount of energy, et cetera. And the size in terms of like hardware area isn't much higher. So other way around. So we have 300-fold, we have 12-fold and 10-fold. And here are the references. So really, for example, this comparison point to another hardware implementation, the reference tree, that came out earlier this year. So it's they just didn't do this, like careful internal optimization. So I was already touching on this, but perhaps it's good to give like a little bit of an intuition what hashes are computationally. So SHA-3 is of course based on the Sketchup 1600-bit permutation. So on a Cortex M4, that would be roughly 10,000 cycles. It's pretty slow, especially on a 32-bit microcontroller. On a typical CPU, it's like 2,000 or perhaps 1,000 cycles. But in any serious hardware, it's 24 cycles. It can be even less because the critical path is so short that you could do 2 rounds in a single cycle. It would be pretty big in hardware, but it is fast. So if you have a Sketchup module, for example, in your hardware, you are spending much more time getting the data in there and out from there rather than running the actual permutation. So copying memory is expensive. So think about it, if a CPU is copying memory, what it needs to do is load from an address, store to another address, then to like increment these addresses, perhaps decrement some loop counter and branch. And for all of these instructions, it needs to fetch the instructions, and so forth. So there's a lot of delay there. So copying one word could be 10 cycles, and here you have to copy a lot of words. So just the mem copy of iteration becomes absolutely the bottleneck. With SHA-2, the situation is similar. So typical hardware implementation, or the one I have in the RTL here, is 64 cycles or 80 cycles in case of SHA-512. In any kind of software implementation, it's thousands of cycles just to do one compression function. So you have to do one compression function even if you're hashing just one byte. And most of these hashes in SLH DSA are just one compression function. So like I said, these are designed to hash input data, not hash other hashes. All of the cycles are wasted on setting up stuff. So when I'm teaching this stuff, I try to present a methodology, and that's of course to perform quantitative analysis, like count all of the primitive operations that your hardware does, and then focus your resources on the things that matter and optimize those. So paper has exact counts of various like primitive hash operations that are done in SLH DSA to give like a rational bytes, optimizing specific things. And of course, we automate the sort of formatting of these hashes. So there's a thing called address in each one of these hashes. So that's done in hardware. So there's a couple of things that are optimized. Perhaps the most important one is this winterness iteration. So here we are hashing hashes in a sort of a loop while incrementing an address. So this is automatic. So you need to set this up once, and it's able to do your 10 iterations of hashing in, let's say, if each hash is 24 cycles, then there's one additional cycle to set up. So doing 10 iterations would be 250 hashes. So this is like an important hardware feature that really speeds things up. But again, it doesn't really grow the size of the implementation. You still have to have a single hash unit in there doing the hardware. So I have briefly like all of the things. So there's 6, I think, primitive hash formats in SLH DSA. It's kind of complicated. So here's like an analysis of public and secret variables. So we have only a single thing that's really coming from the secret key, which is the skprf in the prf message. Otherwise, PK seed, public key seed, the other hash formats are pretty much public information. Okay, it's actually in PRF. There's another variable from the secret key there in PRF. So this kind of shows that not all of these functions require side-channel security. So most of these are public. If you could, there's no secrets going on in majority of hashes. Well, even in signing operations. So there's no need to mask all of them. But a few of them, especially PRF, you need to actually protect or find some other method of protecting it. I'll go a little bit fast now. I went backwards. Here's some more. So I think there's 6 total of different primitive functions. And each one of those has 2 variants, one kind of a format for SHA-2 and another one for SHA-3. And furthermore, on different security levels, you are doing the padding a little bit differently, perhaps using SHA-512 in some functions. So all of this is, by the way, now in hardware. So it's just a bunch of wires and muxes to set up the hashes and make it work. We can now do this because it's FIPS 205. It's supposed to be fixed forever. So we can actually do the same thing as we did with other FIPS standards like AES, just stick the S boxes in hardware. We can now reasonably do this and fix these things in hardware, especially because it makes a lot of sense. So here was what I was talking about, the quantitative analysis, like actual counts of each one of these operations. One can see that, let's say for the 128F function, so this is for signature generation, there's a total of 104,000 hashes going on to create a single signature. Something like 94% are with the F function. And furthermore, at the last line, because F, the hash formatting F is used for a couple of different things, about 87.8% of those are in the hash chaining function. So that is absolutely important. That is one bottleneck that once you eliminate, you are a lot faster, and then some other things become bottlenecks. So this is like how quantitative approach works. I work in RISC-V, so this is like a textbook case of it to do this analysis and work on that. So there's actually a couple of functions which are only used once, which is like, for example, the input hash message. So don't worry about that. Now going a little bit faster again. Okay, actually going backwards now. Here's verify, no secret variables, obviously, so another sort of count. But again, chaining is really important. So the last line, 95% of hashes are just hashes of immediate before hash. Then one observation here is, by the way, that the small parameter sets actually have fewer hashes. You have only 6,000 hashes. On the small set, you have 2,000 hashes total. On the fast one, you have 6,000 times total. So for verification purposes, actually the small parameter sets is 3 times faster. So this is something that is often missed when people are working with these. Anyway, so it's written from scratch. I did it immediately after I left my previous workplace. So it's patent-free. It's BSD 3 clause. There's no patents in the pipeline, so you should be able to use this freely. So hardware, software code is all available. It's pretty small. You don't need much RAM. And it was written so that we can drop it into these root of trust units like OpenTitan later. It will need some modification, of course. So a little bit about the hardware architecture. I'll skim through this. So it has its own register map. This is like a 80s like a home computer architecturally. You poke into these registers to make things happen. But that's what root of trust units are like. Then there's a comparative analysis of the sizes of different hashes. So this might be useful in some kind of discussion about what parameter sets you want to support. Some things are much bigger than others. And the mask implementation of Keccak is 3 times bigger than anything else. It is massive. If you want to mask Keccak, you can do it fast. It's still 24 cycles, a little bit more cycles to set things up, but it is going to be 3 times the size of anything anything else. So that's, again, useful data, I think, for people. Now, really quickly about the side channel stuff. There's one master secret. There's really one n byte thing, which is the SK seed, which is a master secret that opens all doors. And this is used in a lot of hashes in the signing process. That means a single signature will leak a lot of data. So in order to attack SLH DSA, you just need often one trace because the same secret is used over and over again so many times that it just leaks a lot of things. This implementation doesn't have fault attack protection, so too bad. Massive leakage without protection. Leakage gone with protection. So this is standard TVLA analysis. Then we have some performance numbers again, sizes, comparisons, coming to the end, I hope, soon. Final notes. You can make it faster, 10 times faster with that. There's side channel security findings. We have threshold implementation of Keccaks. There's some other ideas about how to protect SLH DSA in the paper, like just modifying the signing function so that the verification function actually doesn't need to be modified, but make it compatible in some other ways. And the future research is in fault attacks. So that's it. By my time, I have 1 minute.
Thank you, Marcus. If you have a question, please come up to one of the microphones.
Thanks for the great talk. So I have one question. Have you looked if you can apply that to MPC and D-head signature schemes, because they do a zillion of shake calls inside? I was wondering if there's something to do.
Wow. So I mean, this is quite complex to do in hardware. MPC in the head, my only observation I've made is that they are extremely complex, and quite often I have utmost respect for the implementers, so that they are able to do that. I'm sure that they would be much faster if you somehow created logic for them that do it natively. But other than that, I don't know.
Okay, thanks.
Yeah, I was wondering whether you're hard coding to FIPS 205 or whether you can kind of reuse the logic for Winternet's kind of chaining hash in other contexts with your accelerator.
So there's like a one core permutation or one core compression function, and then there's like different padding modes. So you can use it and these padding modes are just a bunch of muxes and wires going around. So it's actually not much bigger. So by doing like XMSS or LMS, for example, with this would not be very difficult. Actually, the XMSS formats are quite similar to what is in here. So it's more about the general idea, getting prior art so people can implement it. So yeah, cool. All right, thank you.
Thank you, Markku. The next talk in the session is on MPC in the head using the subfield bilinear collision problem, and our speaker is Yana Kuth.
Thank you for the introduction. So this is joint work with Antoine Joux. And as the title says, I will be talking about the subfield bilinear collision problem, which most of you probably have never heard of before because this is the name we came up with for this. So I want to start by giving a short introduction to this problem and then show you how we can use it to build a signature. So subfield bilinear collision, or SBC problem for short, has three parameters. We have Q, which is a prime or a prime power, and two positive integers, K and N. Now with Q and K, we consider this a tower of field extensions where we have the base field FQ, and on top of it, the extension field FQ to the K. Now, in the SBC problem, we are given two vectors u and v, which have entries in this field extension FQ to the K, and which have dimension n. And then the goal is to find two vectors x and y, also of dimension n, but with entries in the base field FQ, such that the following bilinear relation holds. We want that the scalar product of u and x times the scalar product of v and y equals the scalar product of u and y times the scalar product of v and x. Now, if you look at this equation for a minute, I guess you will see that we have to exclude some trivial cases from the set of valid solutions. So first thing we note is if the vectors x and y are collinear, then this equation always holds. So we exclude this. And also, if the vectors u and v are linearly dependent over the base field FQ, we can also easily find such vectors x and y. So we also exclude this case in the setup. If all of those conditions are fulfilled and this equation holds, then we just say that the vectors x, y solve this SBC problem given by u and v. And as far as we know, this problem first came up, or a version of it first came up in a discrete log algorithm by Joux and Pierrot from 2019, where basically a version of this problem is the bottleneck in computing discrete logs in small characteristic finite fields. And it seems hard to solve if n is large for n roughly k/2. So we want to build an MPC protocol based on this SBC problem. And for that, we do an observation that we can use a certain type of polynomial to test for this SPC equation. So let's say we have such an instance and such a solution, xy. Then we see here that we have basically 4 scalar products that appear in this equation. 2 of those contain x and 2 contain y. Now, if you just pick 4 random coefficients, let's call them x1, x2, y1, y2. And as the scalar products, those will also be elements of fq to the k. Then we can construct this polynomial here, given by these 4 parentheses. And you can basically think about each of those 4 values is being used to just hide one of those 4 scalar product values. So if we then just multiply everything out and simplify this polynomial, we see that it has the following form. So it has some constant coefficient, let's just call it a, some linear coefficient b. Both will, of course, depend on the choice of our random values, as well as on the instance, so on x, y, and on u and v. But the crucial observation is what happens with the quadratic term. And we see that this term vanishes if the vectors x, y solve this SPC problem. Of course, also if the other conditions are fulfilled, but I will get to that later. So this means this polynomial has degree at most 1 if x and y solves this SPC problem. And we will use this fact now to construct a MPC protocol, which does this polynomial test, basically. We have a protocol between n parties. And to do this polynomial test, we basically need to share all of the values that we use in f. And we have to share also the coefficients a and b that we claim this f looks like. So for such an instance, we need sharings of those 8 values, so of the vectors x, y, and of the finite field elements x1, x2, y1, y2, as well as a and b. So each of those will just be additive sharings. And then we send to those n parties. So each of them will just receive the share corresponding to one of those n sharings of all of those values. And then the parties can perform the following MPC protocol. So first, they just create a random evaluation point t0. Then they evaluate the polynomial f at that point. And they evaluate a plus b t0. And if those 2 values are equal to each other, then the parties accept, and otherwise they reject. Now, a few observations about this. First, we note that this protocol is n-1 private, meaning that even having the views of n-1 out of those n parties does not reveal anything about the secret xy. And we also note that this protocol has a false positive rate, because if we assume that xy actually do not solve this SPC problem, well, then this polynomial f has degree 2 and not 1. However, it can still coincide with any linear polynomial of the form a plus bt for at most 2 values, which are elements in fq to the k, which is why the false positive rate is bounded by 2 over q to the k. Now we can use the MPC in the head paradigm to turn this into an interactive protocol, into a sigma protocol between a prover and a verifier, where the prover wants to convince the verifier that she actually knows such a witness of xy of this SPC problem. Now, to do this, she just simulates in her head the execution of this protocol between n parties, and she commits to it in the following way. So she sends a commitment to the views of all of the parties in this protocol. as well as sending the values of those 4 parentheses that she used in F, and the evaluation point T0. And after she sent this to the verifier, he just samples a random index, let's call it I star, between 1 and n, and sends it back. Now this index will just correspond to one of those n parties. And the prover will just respond by sending back all of the information that is necessary for the verifier to compute all of the views, except for the view of party I star. And since the protocol was n-1 private, this does not reveal any information about the secret XY. And after receiving those views, the verifier just checks if those are actually consistent with an honest execution of this protocol. And he checks if indeed we have this equality that f of T0 equals a plus b T0. So if it does, he accepts, and otherwise he rejects. Now, if we have a malicious prover, she might cheat by guessing the value of I star, so of this challenge in advance, and by basically corrupting the view of this party I star in such a way that after she opens the views, this will actually lead to a accepting output, because she can just send those 4 parenthesis values and T0 such that this is actually fulfilled. So we have an intersection of the quadratic and linear polynomial at T0. However, she will get caught if this I is not equal to I star. So this means the soundness error of this protocol is 1 over n plus 2 over q to the k, which was the false positive rate. So one quick thing about the commitment. So we can basically initialize a punctual PRF using the commonly known GGM trees. And the idea there is just to build a binary tree of depth log n, having n leaves, where n is the number of parties. And in our case, each of those leaves will just correspond to one of the n shares, in this case of x. And from those leaves, we can also derive the other values we need in the protocol. So the shares of the vector y of the 4 random values, x1, x2, y1, y2, and of the coefficients a and b. Now, the thing is, if we use this method, those shares in general won't add up to the value we want them to be. So we have to correct them. Oh, I think it's a bit cut off. We have to correct them by sending offsets. And those offsets are needed to correct the values for the vector x, y, and for the coefficients a and b. And those also have to be sent to the verifier, of course. But I also want to note that we don't need offsets for the other values, x1, x2, y1, y2, because this polynomial testing that we do basically works for any choice of those random values. So we just use the value that we obtain by adding up all of those shares, and we don't have to correct it in any way. So now, after receiving this index I star, the prover just computes the path from the root of this binary tree to I star, and just sends back all of the nodes corresponding to the siblings of the nodes in that path. Because using the length doubling PRG that is used to derive the next level here, the verifier can also use it to basically recompute all of the shares for all of the parties except for party I star. And by that, we can basically open this punctual PRF by sending just log of n nodes of this tree. And we can also, of course, now use the Fiat-Shamir transformation to turn this Sigma protocol into a signature scheme by making it non-interactive. And we can also just do tau repetitions of this protocol to amplify the soundness to our desired security level. So in the signature, we then have to include the following values. So we need, of course, one commitment, which can correspond to all of the tau rounds at once. Also, we include for each of the rounds the offsets, so all of those delta values for x, y, a, and b. And we have to include the 4 values of the parentheses that are used in F, which of course are just elements in FQ to the K. Then we also send T0 and of course the opening of the GGM tree. And if we include all of this in the signature, we get the following performance. So for the security level of 128 bits, we can, for example, choose the binary base field F2 with the extension degree 257 and vectors of dimension 130. I just want to quickly mention where this 130 comes from. So from the techniques I showed you so far, 128 would suffice here. However, this 130 comes from a variant of the scheme that we called normalized SPC problem, which basically deals with the issue that we need those vectors x and y to be non-collinear. And to basically not needing to check this, but to inherently have this condition fulfilled, we just require that the vector x ends with 1, 0, and y ends with 0, 1. Because then inherently they are non-collinear. But of course, this reduces the degrees of freedom by 2. So we use vectors of 130 here. And with those parameters, we get the following signature size and running times, depending on the number of parties n and the number of rounds tau. So we see that we get signature sizes between around 5.4 and 3.7 kilobytes, while having signing and verification times between around 1 to roughly 20 milliseconds. And I also wanted to say that those numbers actually are from a slightly more improved version of the scheme, which uses methods that I didn't have time to talk about here. I just want to quickly mention them. And I also want to say that we did include an artifact of this signature, which is already online. And on there, we also use all of those different methods. So one of them is that we use so-called correlated GGM trees, just to make sure that the initial tree that we construct actually yields an exact sharing of, in this case, the vector x. And by using a XOR preserving tree. And by doing this, we can basically get rid of this offset delta x for every round, which decreases the signature size, of course. Also, we did use a method to construct those GGM trees based on AES instead of, for example, using a salted hash function like SHA. Because by utilizing the AES instructions on many processors, this leads to a significant speed up in the running times. And we also did, as far as we know, improve the state-of-the-art so-called hypercube folding, which to derive the shares for the hypercube version of this MPC scheme, we did use a algorithm that basically computes this sharing in running time O of big N, where N is the number of parties. And this led to a speed of around 50%, at least for the large values of N, so for 2 to the 16 parties. And yeah, all of those versions and all of those numbers are included in the ePIN version and also available on the artifact. And that's all. Thank you.
Thank you, Yannick. We have time for some questions.
Thanks for the nice talk. Can you say something about the security against quantum adversaries? Because I mean, this seems related to discrete log, and classically we have much faster, smaller.
Right, of course. Yeah, so it is related to discrete log, but only in one way, as far as we know. So if we solve this SPC problem, we can improve discrete log computations, but we don't see how the other implication works. So let's say even if we have a index calculus oracle or even discrete log oracle, we don't see how this could help us to solve this SPC problem. So of course, we didn't have a full analysis on the post-quantum security yet, but it seems like the best thing we have is just using Grover's algorithm to solve this, which is not fast.
But can you relate it to some conjectured?
Yeah, we have tried to also maybe relate it to subset sum or min rank, but we didn't do the full analysis yet. It seems kind of hard to get this subfield relation, including the conditions that we need, into this reduction, but it seems feasible to do. So yeah, but that's probably subject to future work.
Okay, thank you.
Thanks for the nice talk. I also have a quick question. So this value T0, to get the false positive rate that you stated, you need to choose it at random. And how is it ensured that it's just that this value is chosen at random?
We can just derive it from the input shares of all of the parties using a random oracle, for example.
Okay.
So yeah. I mean, we just want to avoid that the adversary can choose it to be the root of the difference of those polynomials.
Right. So basically, that's essentially similar to the SD in the head scheme.
Right. Yes.
Which basically starts out as a five-round scheme. So you could
Yes,
also state
yes.
this as a Fiat-Tremere transformation of a five-round scheme.
Exactly. Yes.
Okay. Thanks.
Yeah.
All right, thank you very much, Yannick.
Thanks.
Can you hear me? Is it better? Yeah. Yeah. Yes, sir.
The next speaker in this session is Anand Kumar Narayanan, and he'll be speaking about on-round enumeration for special sound multi-round identification and the generality of the hypercube for a multi-party computation in the head.
Thank you. As Douglas just mentioned, I'm Anand from Sandbox AQ, and I'm going to present joint work with Andreas from Eindhoven University of Technology and Sandbox AQ, Christian from Technical University of Denmark, and David from Sandbox AQ as well. And if the title sounds difficult to parse, fair warning, most of the talk will be on QROM security of Fiat-Shamir of multi-ROM protocols with some applications to signatures. Okay, onwards we go. Okay. So a very popular recipe to conjure up post-quantum signatures is that you start with an identification scheme, which is of the form of commit and response. Here, all the verifier does is generate random challenges. And for these, you can convert them into a non-interactive protocol using the Fiat-Shamir transformation, where Fiat-Shamir replaces these challenges with independent hash values of the messages so far, right? So starting from an identification scheme, you end up with a non-interactive scheme. But in the standard model, these are terribly hard to analyze. So we resort to ROM, wherein the hash functions are recast as query random oracle access to these random functions. So of late, we have to grant the possibility that there are quantum adversaries. So there's been a lot of progress in the past decade or so, wherein you can model quantum adversaries by giving them access to these random functions in terms of a quantum random oracle, wherein they can ask for arbitrary superposition queries. Okay, and in this talk, we will analyze certain schemes under the QROM. In fact, we will analyze them in a slightly more demanding model called as the EQROM, but pay no mind, it's not that important for the talk right now. Okay, so as I mentioned, QROM has been around for a decade or so, and there is rich progress, but our story is going to start with Don, Fair, Mayans, and Schaffner, who proved optimal QROM security for Fiat-Shamir transformations of 3-round commit and open protocols, right? So, but if you look to more rounds, say 5 or more rounds, only much looser bounds were known. Until Aguilar, Melchor, Huil-Singh, Joseph, Mayans, Ronan, and Yu, they looked at one particular MPC in the head scheme called as syndrome decoding in the head. And they tailored a QROM proof to that scheme, which was very tight. And the way they did it is they took this 5-round scheme and eliminated one of the rounds to result in a 3-round scheme. And they did so while preserving soundness and zero knowledge. And the moment they got down to a 3-round scheme, they could invoke the aforementioned work of Don, Fair, Mayans, and Schaffner and get very good points. So this begs the question, does this round elimination analysis generalize, and if so, how far? So the main technical result of our paper is a generalization of this round elimination analysis to 5 or more rounds. But for ease of exposition, I will only speak of 5 rounds in the talk, but our paper is written in much greater generality. Apologies, I have a sore throat. And we hope to add a remark soon about protocols with, say, 7 rounds, wherein our bounds are quite nice. Right? But today, just 5 rounds. And so the good thing is, for very many schemes with 5 rounds, such as all the NIST MPC in the head protocols, our bounds are tight. And we leverage this to come up with another application to MPC in the head-based signatures, wherein we can augment them with what's called as the hypercube optimization. So this is a very intricate technique that speeds up resulting signatures by, say, 10-fold. Right? So it's a very practical scheme, and we will use our round elimination to show how this is in some sense universal to all the MPC in head schemes. Okay? So on to a slightly more detailed expression of our results. So as I mentioned, we're going to do some kind of a round elimination from 5 to 3 rounds. So what can we say about soundness? So our results are going to bound something called as frac S soundness. It's that funny looking thing over there, but don't fret. Just think of special soundness. So this frac S soundness is a generalization of special soundness, and it's really expressive. So for instance, it can accommodate crazy challenge patterns that arise out of parallel repetition, where In some of the repetitions, you do something, and in the others, you do crazy stuff. But for our talk, we will get down to 3 rounds and prove some generalization of special soundness. But just think of special soundness. So our theorem will be a general expression for the computational version of this Bragg soundness. Sadly, however, the quality of our bounds depends on the identification scheme. So it's not a universal result. But I would like to highlight one particularly nice scenario wherein we get really good bounds. And to appreciate this scenario, imagine granting the adversary the ability to choose the first message at will, all right? And then you draw the first challenge uniformly. And if you look at what remains, it's nice to think of it as a distribution over 3-round protocols, wherein the randomness in the distribution comes from the choice of the first challenge, right? The adversary gets to choose the first message, so that's quite dangerous for the security of a protocol. But we can leverage the randomness in the first challenge. So if in the resulting distribution, with very high probability, we have some kind of a special soundness for the 3-round scheme, then our bounds are really tight. So you can think of it as a sufficient condition where all goes well, right? And thankfully for all the MPC in the head schemes, in the NIST on-ramp signature scheme, this happens. Sadly, there are schemes, even 5 rounds, where our bounds don't tell much, right? So one instance is MQDSS. This is an identification scheme based on the hardness of multivariate hard problems. And you can prove that these are sound by other means, but when we go through our analysis, we get vacuous bounds. And sort of the reason is that in that particular case, if we let the adversary choose the first message at will, there is no soundness that remains. So when our method works is when the 5-round protocol somehow factors wherein there is soundness that can be leveraged between the first challenge and the second challenge, as pictured here. Okay? So let's take a quick look at how we prove our bounds. So we have a picture of a 5-round to 3-round reduction. No surprises here, just the usual stuff. And as I hinted before, we would like to say something about the special soundness of the 3-round protocol on the right. But we would like to quantify that using certain statistics of the original 5-round protocol. Okay? To better appreciate those statistics, look at an adversary who is interacting with the verifier in the 5-round scheme. Excuse me. And think of the adversary producing a bunch of transcripts, say to feed to some extractor. And consider the quantity wherein the adversary gets to maximize over the choice of the first message, the expectation over the choice of the first challenge, this particular quantity. And this quantity is the probability of cheating the protocol conditioned on seeing W1 as the first message and C1 as the first challenge. And what do I mean by cheating here? You can think of it as an adversary who produces transcripts that pass verification, yet some extraction structure you have in mind fails, right? So mu is this first moment, so you can think of it as a mean over the first challenge with a maximization over the first message. And I'm also going to think of the standard deviation. Everything else is exactly the same. And our methods are going to bound the special soundness of the 3-round scheme using essentially these 2 quantities, okay? And to make the analysis, look at an adversary for the 3-round scheme. And the adversary now has quantum access to the random oracle. And let's say that she is bound to at most Q queries. And these can be superposition queries, arbitrary queries, right? And it sort of turns out that the best she can do is somehow search for a first message, W1, right, that lets her cheat with high probability. And so technically, the question is this search possible? Like, can you somehow search for a first message that renders this 3-round scheme fairly easy? And our main technical theorem is a quantification of how hard it is to search, right? So what we prove is that if we have an adversary playing the game with a 3-round protocol, then the expected probability of cheating conditioned on the first round being W1 is bounded by this expression. And this is a function of the 2 moments mu and sigma, and also the number of queries that we upload. Right? So once you have this technical lemma, you can prove a bunch of things. So why is this true? To sort of appreciate what's happening here, let's look at the function that is being bounded. And if you think of it as a function of the first message W1, right? It's actually a function of W1 and the value of W1 under the random oracle. And we are trying to maximize this function whose inputs are outputs of the random oracle. And thankfully, there are very precise bounds that tell you how hard it is to do this. Right? So you have W1 as an input, you feed it to a random oracle, and you have to find the value, RO of W1. And then this pair of values are fed to the actual functions of interest to us. And we want to do some kind of an expectation maximization, or at least find large values. And these 2 results tell us that it's hard to sort of optimize functions wherein the inputs come from values of the random oracle. Right? So this is our main technical result. What does this give us? So for instance, now if I take a 5-round scheme, say a parallel repeated 5-round scheme, which is D-sound, and we reduce it to 3 rounds, then the additional advantage that the adversary gains by having Q superposition queries is bounded by this query term. Okay? So this is our soundness preservation. What about zero knowledge? And the picture is much nicer as the slide is quite sparse. And here we can unconditionally prove that zero knowledge is preserved without any caveats. And this is largely thanks to an adaptive reprogramming lemma of Grillo, Hubelmans, Hulsing, and Mayans. Okay, so on to our application as promised. And of course, we have the familiar MPC in the head regime, wherein you can build identification schemes out of multi-party computation. In our context, what happens is that you associate a function f with a public key, right? And the prover claims knowledge of a secret such that it's a satisfying assignment to the function. By satisfying, I just mean you plug it in and you get 0. And there's a simple way the prover can prove this claim. What she does is she shares the secret among a few parties in her head and does an MPC computation that evaluates the function in question, right? And then she commits to the views of the parties and the computation itself. And the verifier asks for all but one of the views, and then the prover obliges. And the verifier checks consistency, and that computation goes through. In a sense, the only way the prover can cheat is if she can guess which player the verifier didn't care about. And that happens with probability 1 over the number of players, which can be boosted to any extent that you desire. Okay, so there is an aggregation scheme called as the hypercube aggregation. I'm not going to tell you what it is, but convince you that it is quite effective and quite beautiful by throwing you pictures from the original scheme. But what you gain is roughly a 10-fold speed up in both signing and verification times. And so this was first introduced by Aguilar Melchor, Gama, Hope, Wilsing, Joseph, and Yu. And what they did was came up with this optimization for one particular scheme called as syndrome decoding in the head. And trying to take advantage of the speedups, several other MPC in the head schemes have tried to adapt it to their own system. But they've all done so in a white box manner, wherein they opened their system and looked at everything and tried to make things work. What we do instead is we start from an abstraction. And so this is going to be a 3-round MPC in the head protocol, wherein we constrain the MPC in question to be symmetric and n-1 private, and also additive. And these are not very strict constraints, so don't worry. The biggest constraint is that it's a 3-round MPC in the head scheme. And once you have an MPC in the head scheme in this abstraction, we show how to generically incorporate the hypercube optimization while provably preserving soundness and zero knowledge, right? So I'm almost done with the talk, except I'm not. Sadly, most of the MPC in the head schemes, which account for 1/4 of all NIST on-ramp signatures, are 5-round and not 3-round, right? And part of the reason is that they leverage hard problems that are mostly linear with some non-linearity thrown in. So if you look at syndrome decoding, it asks for solutions of underdetermined linear systems over a finite field with some non-linearity constraint, such as sparsity, which asks for low Hamming weight solutions. And these systems have a proof wherein in the early rounds you prove linearity, and in the later rounds you prove multiplicity, right? So, but these are 5-round schemes, and so they don't fall into our 3-round abstraction, right? So what can we do? So thankfully, our round elimination comes to the rescue, and we show that we can reduce all these schemes to a 3-round scheme, and thankfully they fall into our abstraction, and we can apply the hypercube technique. We actually only spell this out for one particular scheme called RIDE, but it's a very, very simple blueprint to follow. So if you desire to incorporate hypercube into your 5-round MPC in the head scheme, it's a very simple translation, and you're done. And I have 1.5 minutes left, and I'm happy to take not too difficult questions. Thank you.
Hi, thanks for the talk. I just wondered if you need any notion of collapse binding.
Collapse what?
Collapse binding for the messages, like a collapsing SIMO protocol, or do you need that? If you know what I mean, like last.
I do not know the technical term. If you could explain it in simpler terms, please.
I've seen that there's a counterexample for just special sound protocols. When you apply the Fiat-Schmidt transform, it's not enough.
Yeah.
And then they're using this unreal notion of collapsing, like the last message, you collapse bound to it. And then I've seen works by Christian and others that can, like, with the measure reprogram, right? Then they have, collapsing.
Okay.
Yeah, so is that something you require?
I have to say that we don't require it.
Okay.
So, but I have to look at the particular example. I'm not sure what the answer is. We don't use measure and reprogram techniques.
No, okay, so it's like a...
Mostly it's online extraction. The main theorems follow from that.
So does that mean it's like a subset of special sound protocols?
No. It's a superset of special sound protocols.
Oh, but what about this counterexample then?
For 5 rounds?
I'm not so sure about the counterexample.
Okay, so the thing is, if you have a higher number of rounds, you can do a round reduction inductively or recursively, the way you see it. And in this case, so once you do one round elimination and you get to the next one, you have a new protocol whose statistics you have to talk about. And there you have to do a little bit of finessing so that the induction goes through. Perhaps that's where it fails. So.
Okay, very cool.
But for 5 rounds, if it falls in that scheme, it'll work. And there's also a chance that the scheme that you're talking about gives just trivial bounds and says that the adversary can cheat with probability at most 1.
Yeah, maybe.
Right, so.
Yeah.
So it's a
Okay.
general tool and it applies in certain cases.
Okay, very cool. Thank you.
Thank you very much.
Hi. Okay. All right. Oh yeah. It's a bit counterintuitive.
The final talk in this session is by Laurent Marceau, and the topic is solving the tensor isomorphism problem on special orbits with low rank points.
Thank you. So yeah, this is joint work with Valerie Gilchrist, Christophe Petit, and Gang Tang. The title is a bit long, so I won't repeat it. So we all know that public key cryptography relies on the harness of some mathematical problems, namely discrete log and factoring, and then in the presence of quantum computers, these become easy. And so like post-quantum cryptography, on the other hand, we've seen like quite a variety of problems. So lattices, hashes, isogenies, codes, and multivariate mainly. And in cryptography, as well as in life, diversity of assumptions matters. We've seen quite some major attacks recently, namely on Rainbow, on SIGH and Psych, and there was a bit of a scary e-print recently as well. That was fine in the end. So in this talk, we looked at a new post-quantum assumption that is based on the harness of some tensor-based problem, and namely, we looked at the cryptanalysis of a commitment scheme. So in this talk, I'll talk about a cryptanalysis of the tensor-based commitment scheme of D'Alconso, Flamini, and Gangemi, which was at Asia Crypt 23. We give a polynomial time attack on the decisional tensor isomorphism problem on special orbits, which breaks the hiding property of the commitment scheme. We extend it as well on a polynomial time attack on the computational version of the scheme. And the main tools that we use are low rank points on tensors and the knowledge of their stabilizer subgroups. And I'll also give some sort of intuition on the repair that we propose as well, that uses random tensors. All right, so let me introduce you to tensor-based cryptography. So the elements that we look at are three tensors. So some elements V in FQ to the n, tensor FQ to the n, tensor FQ to the n. And then you can decompose them as a sum over three variable ijk from 1 to n with some coefficients. And then you just look at the tensor of the canonical basis. And you can also represent it at a list of matrices. So n matrices in Mn over Fq, so n by n matrices over Fq, by kind of projecting on one coordinate. And so, for example, if you consider the tensor product of these three vectors, you kind of have, so here you have zeros, and then you kind of observe that that's why these two matrices are zeros, and then these coefficients you can kind of like relate obviously to the other coefficient in the tensors. So these representations will be super useful for the rest of this talk, the other way around. All right, and then to do cryptography, we kind of want a group action. So we look at the group G, which is three copies of GL and Q that acts on our tensor space in the following way. So we take three matrices, our tensor in this like sum of coefficients representation, and then the matrices act by multiplying the element of the canonical basis. So you have, instead of having EI tensor EJ tensor EK, you send it to AI tensor BJ tensor CEK. So this group action is being studied fairly recently by these two papers by Ji Kiao, Song Fu at GCC, and then Brokow, I'm sorry about the name, and Kiao at ITICS 21. So the hard problems are quite natural. You have the decisional tensor isomorphism problems. Given two random tensors, you need to decide whether there exist three matrices that send one to the other. And the computational version asks you to compute these matrices when they exist. And this problem has been shown to be equivalent to the trilinear form equivalence problem and the matrix code equivalence problem, which is the problem that Mads NIST candidate for the signature call relies on. So let me now introduce the bit commitment scheme of D'Alconso, Flamini, and Gangemi. So you start from two special tensors, T0 and T1, which corresponds to the bits B0, 0 or 1 that you want to possibly commit to. So say you want to commit to 0, you start from T0, you compute the action of three matrices A, B, C that send you to another element in the orbit of T0, and this element C will be your commitment, which you publish and then you forget about it. And then when you want to open, you just provide the three matrices and everything, and you check that everything works out. So the requirements, you need the two starting tensors to be in two different orbits for the binding property. Otherwise, the person who sends the commitment can cheat. But it's hard to verify that two random tensors are in different orbits. So what they do in their paper is they start from two special tensors, and they come up with some invariant that they can compute on them, and they can check that they are indeed in different orbits. I'll explain that in the next slide. And then for the hiding property, you need that your commitment looks random, because now you kind of have an invariant, so you want to make sure that it's not applicable to the commitment itself. So the invariant that they use is the tensor rank. So a rank 1 tensor is an element of the form A tensor B tensor C for ABC in FQ to the n. And then in general, the rank of a tensor is the minimal integer such that you can decompose it as a sum of rank 1 tensors. And for random tensor, it's been quite extensively studied, and it's hard, in fact, NP hard to compute. So they start from these two special tensors. So T0 is of the form you sum from I equal 1 to n elements of this form. And then for T1, you sum only up to n minus 1. And then you have this lemma that the group actions kind of preserves the rank. And here you can kind of read out the rank of these tensors fairly easily. You have that T0 as rank n, T1 as rank n minus 1 because they're special and not random. And so you're ensured that they're in different orbits. All right, so let me just recap kind of the structure of the commitment scheme. So you have two public tensors, T0 and T1. And to commit, you sample a random element in your group, you compute the action on the corresponding TB, and you send it. And then to open, you send your bit, the randomness, and you check that everything works out. All right, so what about the security? So binding, you get perfect binding because your elements are in two different orbits. And the hiding property is related to the decisional tensor isomorphism problem. So let me recall this problem. Given two random tensors, V0 and V1, decide whether there exist three matrices that send one to the other. And here, the key element is random, right? We saw that T0 and T1 are chosen in a specific way, so it's natural to ask, how random are they, and are they random enough for this problem to remain hard? So this is an example for n equal 4 and q equal 11. So TBs of the form, you've got 1 here, 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 and then here you get 1 when it's T0, and you get 0 when it's T1. So this looks quite far from a random tensor, right? But as a sanity check, maybe we can look at, when we apply the group action, maybe it's all good and the result is random. So if you look at like 3 random matrices, you apply it to T0, you do get something quite random. But our intuition here was like, well, there's still a lot of structure going on here, so surely there's some that gets translated to the commitment, and we can do something about it. So let me introduce the first tool, which is the rank of points on tensors. So you start with the tensor in matrix form, or like list of matrix form. So you're represented as n matrices M1 to Mn. And then the rank of a point, U, becomes the matrix rank of this linear combination. So U1 corresponds to the first element of your point times the first matrix, and so on until UN Mn. And then, for example, if we go back to our example of before, if you have like a point U in F11 to the fourth, its rank in T0 will be the rank of this diagonal matrix here, and the rank in T1 will be the rank of this matrix here, where you get that this is 0 because you had a 0 in T1 here. And then you get that the group action preserves the number of points of a given rank. So if you have, I don't know, k rank, well, okay, maybe if you have k points of a certain rank in your starting tensor, you'll have as many in the tensor that you obtain after having applied the group action. So if we look at ranks of points of rank 0, which is the most natural thing to do, you get that you have a point of rank 0 in T0 if this matrix here shown for n equal 4, but in general, I think you can kind of see what it would look like for dimension n as rank 0, which is kind of equivalent to having the U being the 0 vector. So if you kind of ignore that, you get that T0 doesn't have any non-trivial rank 0 point. And then if you look at T1, you get that it will have, up to scalar multiplication, only one point of rank 0, which will be the nth canonical vector En. And you can generalize that to like kind of any element of this form, and you get that the points of rank 0 will be a vector space of dimension B. All right, so let me summarize that in the first attack. So our goal is, given the commitment C, which is obtained as 3 matrices A, B, C applied on some tensor TB, recover B. So the first key thing is, well, the group action preserves the number of points of rank K, and we know this exact number for rank 0 on T0 and T1. So really all we need to do is just compute the number of rank 0 point on our commitment to decide. And it turns out that this is quite easy to do. You just write it as in matrix form. You solve a linear system. If you have a solution, it means the bit was 1. Otherwise, the bit was 0. And for the first parameter set, it's just a couple seconds on the laptop. And for the biggest parameter set, it's about 14 minutes, which is less than the length of this talk. So the takeaways of the attack, well, this breaks the hiding property of the commitment scheme. It shows that the decisional tensor isomorphism problem is easy when you have orbits with low rank points. In general, it is not. So we have 2 natural questions that we looked at. What about the computational version? Can we do something about it? Is it also easy to solve on these special orbits? And like how likely is it for a tensor to have low rank points? So like how applicable is this attack in general? So let me briefly outline the attack on the computational version. So this time we're given the commitment and we want to compute the 3 matrices. We've solved the decisional problem, so we can assume we know B. So the naive strategy is, okay, you just put it in a Grobner basis and you try to solve, but you can see that the number of solutions blows up very quickly with the dimension and the size of and the characteristics, of the underlying field. So now you turn to rank 1 points, and you use an extra tool, which is the knowledge of the stabilizer subgroups. So all the elements of your group that send TB to itself to kind of narrow down the space of solutions and go to a unique solution. So the first step is, well, you compute the rank 1 points of T0. There's n of them that kind of corresponds to the vector of the canonical basis up to scalars once again. And then you do the same thing on your commitments. You can compute that fairly efficiently using min rank, and you get these 2 sets of rank 1 points. And then you have this lemma that tells you that there is some ordering of these set of points that corresponds to a matrix A that sends the rank 1 point of T0 on those of C. And so you don't really care about this ordering because you're fine with recovering an equivalent matrix. And so just by computing them and wringing them out, you already get a matrix A that is equivalent to your starting matrix, because you can show that permutations kind of leave your tensor invariant. Cool. So now you've recovered A. And all is left to do is recover B and C. And then you can just, again, solve a system of linear equations. So you kind of, put things around. So here you have identity bi acting on T0 equals to a minus 1. You've just recovered that identity, and this is another thing you can recover. C here. You can just solve it. And again, you kind of use your knowledge of the stabilizer subgroup to filter out the solutions. Namely, you have some type of diagonal matrix that leave your tensor invariant, so you can fix some things to get down to unique solutions. And you get that you can recover a valid tuple of matrices in O to G and 6 operations. And I've presented everything for T0. In the case of T1, there's a bit more complexity going on, but kind of following the same global strategy, you can do the same thing and recover in similar complexity. All right, let me now quickly give an intuition on how to fix this. So the first thing that we observe is that if you sample tensors randomly, you'll almost always be in different orbits with really high probability. And the second observation is that you can prove that random tensors won't have any low rank points, so this attack won't be applicable. So you can kind of tweak the commitment scheme and saying, well, we can just sample random tensors in the setup, and this will be enough. And the price that we pay is that we get statistical binding now instead of perfect binding, and you can remain with computational hiding. And we don't impose any structure on the tensors, so we really do rely on the original version of the decisional tensor isomorphism problem, and we don't introduce any new assumptions. All right, so let me wrap up. So we solved the tensor isomorphism problem by distinguishing the committed bit and computing the matrices. This is only applicable on special orbits with low rank points because we exploit the underlying structure of the starting tensors T0 and T1. We give 2 polynomial time attacks that completely break the commitment scheme. And we propose an alternative commitment scheme from random tensors. And that's it for me, and there's a lot more detail in the ePrint if you want to check it out. Thank you.
Thank you very much for the nice talk. Have you thought about finding structured tensors, starting tensors without low rank points?
Like finding them?
Like you could try to recover a perfect binding by finding, similar simplistic starting tensors without low rank points.
No, we haven't really looked into this. To be fair, the Reaper was kind of like the end, and the main focus was more the cryptanalysis, but this is a really good idea. Thank you.
Thanks.
I have a question. You mentioned that the tensor isomorphism problem is also used in some NIST candidates' meds. Does your attack pose any risk for those signature schemes?
No, because we really do exploit these special orbits, and in the NIST submission they really rely on a more general version, so they're fine. Otherwise, we would have looked into it. This would be a bit more, Yeah, thanks for the question.
All right. Well, thank you very much. Please join me in thanking the speaker again and all the speakers for this session.